basic to kind of build up your knowledge of how SimObjects work, what the architecture of SimObjects is, and then kind of build on top of that with how to do events. And then I think we'll have enough time to do memory operations as well. And if not, then we'll just at least point you to where you can see how to do memory operations and go through that quickly. Then this afternoon, Ayaz is going to take us through, Mayar is going to take us through this morning. And then this afternoon, Ayaz is going to take us through how instruction execution works and adding an instruction. And then tomorrow, we're going to continue with more of caches and then GPU stuff. I know we didn't get to checkpointing yesterday. I think we'll punt that until Friday morning, and we'll spend 30 minutes or so on that on Friday, along with a grab bag of other things that we want to cover. OK, before I turn it over to Mayar, I want to remind you, we once again made some updates to the code spaces. Assuming you got it to work yesterday, and you added the remote upstream, which should look something like this. Give me 1 second. So if you run get remote minus v, you should see something like upstream if you run get remote minus v to list your remotes, you should see the gem5 bootcamp as upstream if you went through what we did yesterday. If so, you ought to be able to do git pull upstream main, and it should work. If not, raise your hand. I see your hand.
I just wanted to say, before you get stash, it's better for us to
Yeah. So yeah, that's definitely true. Instead of stash, if you do git commit and then merge when you pull, then you'll keep everything committed. We should have done a better job of teaching you Git. I blame GitHub code, though, or Classroom. Yeah, raise your hand if this is not working for you, and Kalstov or Bobby or I or somebody else will come by and help. OK, with that, I am going to turn it over to Mayar to teach you all about SimObjects. I think there's going to be a lot of interactive coding here. So I'll be going around this morning, and others as well. And if you have any questions, just let us know, and we will help you keep up with what Mayar is talking about. OK, with that, here's Mayar. Introduce yourself. Okay.
So, hello everyone. I'm Mayar. I'm a PhD student here at UC Davis, and I work with Jason. And today I'm going to tell you how to create your own SimObject. OK. So, I guess Jason took care of this. But before we do anything, I want you all to run this command in green inside the gem5 directory. We're going to build gem5 for the null ISA, which is basically no ISA. And we're going to build our work on top of this. So I want everyone to run this on their code space right now.
Give everybody an identity code space.
OK.
I'm sitting back here watching people loading code space.
OK. Sorry. So just as a note, in the slides, everything that is green is a command that you have to run. So if I tell you to run something and you're in a slide, and if you're looking for it, look for the green stuff. And hopefully I haven't missed anything. Costa? Can you go to the back and see if you can hear me? Okay. So I'm assuming some of you have started the compilation process, and we're going to get started while the code is getting compiled. So first of all, let's talk about SimObjects and what they are. Basically everything that, so not everything, but almost everything that you find in the gem5 code space is a SimObject. And SimObjects are basically the representative for real hardware. They are fundamentally the thing that you use to model your hardware. For example, you have, throughout the past 2 days, you have been using timing simple CPU, which is a SimObject. You have been using memory controller, which is a SimObject. You have been using traffic generator, which is a SimObject. You have been using a crossbar, which is a SimObject. One good thing about SimObjects is that they facilitate parameterization. So since they are your model, they allow you to change different variables about them. On top of that, the clocked object, which extends SimObject with a clock. So sequential circuits should be modeled using clocked object. And also, they provide accessor functions for time. So we'll see in the future that we need to calculate absolute time or absolute tick. And clocked object has functions that allow you to calculate the absolute tick for clock cycles. OK, so let's see where the code for a SimObject resides in the gem5 code space. So for every SimObject, there are 4 files. First of all, there's the SimObject file that basically defines the SimObject that you want in the Python world. It defines what parameters your SimObject should have. For example, your cache has a parameter called cache size. So this is where you tell gem5 that I want a model that has a variable cache size, or a variable parameter named cache size. It also defines the connections that your SimObject has. For example, throughout the past 2 days, you have been connecting ports, and this is where you define ports. So if you define a SimObject, the class that you define in Python is used to instantiate an object in your config script. After that, you need 2 C++ files, a header file to define the interface for your SimObject and the functionalities that it has. And you need a source code, a .cc file, to actually implement those functionalities. There's a 4th file that is auto-generated, and you don't have to do anything about it. And it's called a params file, which compiles the parameters that you specify in Python into a C++ object that is understandable by the C++ code that you're going to write. OK, I hope this was not confusing. Is there any question? Great. So let's move on. So what I want you guys to do is to run this command and copy all the boilerplate code that I'm going to provide to you into the gem5 directory. So every C++ code that is compiled from gem5 is in the source directory. So let's copy materials developing gem5 models, 02 SimObj, bootcamp, into gem5 source. I'm going to give you guys 1 minute to do this, and I want a thumbs up from someone who has done it. OK, great. OK, so let's take a look at a SimObject file. Again, as I said, a SimObject file defines a SimObject in the Python realm. And it also defines the tunable parameters that your model should have. So what I want you guys to do is open this file, gem5 source bootcamp hello SimObject.py, and we're going to take a look at that file together. And I'm going to do the same thing too. OK. OK. this is embarrassing because I chastised you for not being ready, and well, it's Jason's fault. The VS Code not being ready. Okay. And I haven't done the same thing too. Oh. Okay. Gem5, and I'm going to do this. Okay. Okay. So you can take a look at this file on your own computer. Ow. Shift. Okay. Okay. Sorry. We're looking at goodbye SimObject. Okay. So I want you guys to look at 4 different things in this file. And these are the things that are Gem5 specific. First of all, I want to say a few things about the SimObject file. You can see that it's written in a Python-like language. But if you run this with a Python interpreter, it does not understand this. It's going to give you errors. However, Gem5 has a specialized Python interpreter that understands this. OK. So let's see what these lines mean. OK. So since we're going to define a SimObject, we need to import the package for SimObject in the Python realm. And that is what line 28 is doing. So it's telling Gem5 that I need the Python implementation for SimObject, because I'm going to inherit from it and implement another SimObject. If you look at line 30, it basically specifies a class called hello SimObject that inherits from SimObject. OK. The next thing that I want you guys to trust me and do as I say is just set the type to the name of your SimObject. I'm not really sure what it is, but trust me and set the type value to the name of your SimObject. The 2 other things that we're looking at here is CXX header and CXX class. So CXX header is the path to the header file that defines your SimObject in C++. For example, for the hello SimObject, it's in gem5 source bootcamp hello SimObject hello-simobject.sh. One thing that I want to note here is that the source directory in gem5 is part of the path, so you can specify any path relative to source. CXX class is the name of the class in the C++. You notice that there's a gem5 : before that, and that is because we implement every SimObject in the gem5 namespace. There are a few namespaces in gem5 code base, and gem5 is the one that holds all the SimObjects. OK. Great. Let's see. OK, any questions from the SimObject file? Uh-huh. Oh, I think it's going to, when you try to compile it, it's just going to give you errors. I'm not really sure. Jason, you can correct me if I'm wrong.
Yeah, it'll give you errors. That's just, you have to specify the fully qualified C++ class that corresponds to this SimObject.
Okay.
In theory, you could use all different names for the
So don't. Oh, sorry.
So you said like the CXX header is relative to source.
You can specify it as relative to source.
Okay.
You can also put the absolute path, I guess.
Yeah, after that. Yeah. I'm just
Yeah.
curious if you kept like a SimObject
Yeah.
outside of source.
Yeah, it's very scalable to put it like as relative to source instead of absolute because you don't. Yeah.
So if you keep it, so actually that's a really good question. If you keep a SimObject outside of source, gem5 has a mechanism called extras that when you build gem5, you can tell it extra source paths to search for things. And in that case, you can put the path relative to that extra. So if you want to keep something outside of the main gem5 tree, there is a mechanism to do it.
Okay. Yeah. Okay, now let's take a look at the header file for the hello SimObject. Which one is this? Okay. Okay. So this is as many lines as you need to define the functionalities of a bare minimum SimObject. I want you guys to pay attention to a few things here. I talked about that magical file that is auto-generated, and I want you guys to trust me that gem5 makes sure that things are done correctly. So one thing that we need to include in this header file is the parameters for the SimObject. And when you compile gem5, gem5 is going to put that in params / the name of your SimObject.sh. The next thing that we need to include is the C++ header file for SimObject, which is in sim/sim_object.sh. Okay. So you can see that I'm putting the definition of that hello SimObject inside the namespace gem5, which corresponds with the CXX class that we defined in Python. So I'm hoping that I can draw parallels between Python and C++ here. So if there's anything that confuses you between these things, like why is it something in Python and why is it something in C++, please ask those questions. Okay, so one thing that makes our, so let's take a look at the constructor of hello SimObject. So every SimObject should define a constructor like this. The constructor should take a const object of its parameters. So we defined hello SimObject. Well, Python defined hello SimObject parameters in params/hello SimObject.sh. And we can use it here to pass it to the constructor of the SimObject. So trust that this is automatically done when you compile gem5. And it's passed here. I want to also mention a really convenient macro. So this params macro basically typecasts hello SimObject params to params. So this is why instead of params, hello SimObject params, you see params here. Okay. Any questions? Sorry. Yeah, I forgot to mention that, but that is an include guard. Do you know what an include guard is? Oh, so I guess I should explain it. So when you have two source files that include each other, you have an A that includes B and B that includes A. This series of includes is going to go on forever. So by doing this trick, you make sure that every file is only included once and this loop is broken. So that, like, you don't end up including two things in a loop. Okay, any other question? Great, let's go back to the slides. Okay, now let's actually implement the functionalities. And I want you guys to take a look at gem5 source bootcamp hello SimObject hello_sim_object.cc. So, as you can see here, again, defining the functionality inside the gem5 namespace. And we only have one function to implement right now, and that is the constructor for our SimObject. Okay. So since hello SimObject inherits from the class SimObject, it has to call the constructor for SimObject. I want you all to open this file. So if you're on Windows, press Control P, and if you're on Mac, press Command P, and type sim_object.h. And you should open the one in gem5 source sim.
Or just go to source sim.
Control P gives you a power to open any file.
Yeah. I just SimObject
yeah.
as well.
Okay. So again, so let's take a look at the constructor of the SimObject class. It takes one argument of the type SimObject params. So if you look at this line, SimObject params is typedef as params. Okay. So I want you guys to look at both the constructor of our SimObject, hello SimObject, and SimObject. Okay. So what we're doing here is passing that object from type hello SimObject params to the constructor of SimObject. So what I want you guys to take away is that gem5 makes sure that hello SimObject params is of the type SimObject params. So this is what gem5 makes sure is done. Hello SimObject inherits from SimObject. Hello SimObject params therefore inherit from SimObject params. Okay. Is that clear enough? Is there any questions? Great. Okay. So let's just print out hello world from a SimObject, and let's put the name of the function inside parentheses for our future reference. So basically what this SimObject is going to do is to instantiate one object, say hello, and be done. Nothing else. Okay. Is there any questions? Okay. So do you guys think that now we can use our SimObject? Can I get an answer? Yes? Yeah. So the answer is no, because we still haven't compiled it, and we still haven't told the compiler to add this SimObject to the list of available SimObjects in the source code. So the way to do that is to add a few lines to a specific file called sconscript. And if you're adding a source code in a directory that there is no sconscript, just simply create a file called sconscript, and scons will find that and take care of the rest. So what I want you guys to do is open the sconscript file next to the files that we have open, but it's in gem5 source bootcamp hello SimObject sconscript. Okay. So this is, I think, the first time you guys are actually going to write code for this SimObject. So let's do that together. I want you guys to follow along and ask as many questions as you can, because this could become confusing real soon. So, okay. I want you guys to also trust me and not ask questions about this line, and put this in every sconscript that you write. So let's put import parentheses, quotes, star as the first line in our sconscript. Okay. So the next thing that we want to tell gem5 is that we have a new SimObject. So let's type SimObject with parentheses. Do I have to scale this up? Can everybody see this clearly? I see a few people trying to reach out. Okay. Oh, okay.
So just in case anyone will, Sloan script is it's kind of like our main file in a sense, except using Sloan, so it's called Sloan script. If that wasn't clear.
Again. So.
I heard this before I joined the project here. It's a main file.
It was super popular in yachts.
No? Yeah. It's based on Python, so it's right in Python.
Yeah. So this SimObject takes two parameters. Let's first specify the name of the name of the Python file that we want to include in the compilation process. So it's going to be hello simobject.py. And as the second parameter, let's provide a list of the SimObjects that are defined inside this file. So that we're going to say sim_objects is equal to, well, hello sim object. Okay. Any questions? Okay. So the next thing that we're going to tell the compiler is where to find the source code. So let's just say source, and then hello _sim_object.cc. So basically, by adding these three lines to the scan script, you have now registered the hello SimObject with the gem5 binary. So the next time you compile gem5, it's going to be added to the binary. So now let's actually go ahead and compile gem5 again. The same command, you can copy and paste it from here. So I want you guys to take a close look at the output of the compilation. You will see like names like hello SimObject pop up when you sorry.
Can I say something while we're waiting?
Yeah.
So I want to mention something real fast while this is building, which I know I didn't ask my art to mention. Thanks. So if you'll notice here and in the SimObject description file, so the way that myr chose snake case with the underscores versus camel case with the capital letters was intentional. So this is part of the gem5 style, that your SimObject, your SimObject Python file is named with camel case. And that's when you can look at a file that's all camel case with a .py, you know that's a SimObject description file. All the source files are all lowercase with underscores in between, or snake case. That way you can look at it and you know it's a source file. Same thing with the SimObject names. These are camel case. And when we get into it, class members are camel case in C++. And local variables are snake case. So that way you can look at a variable without having to go to the header file and know if it's a member variable or a local variable. Yeah, I think that is, was there any other style things in here to mention?
The functions
Functions are,
the next line.
yeah, functions are a little bit weird. So we always do a new line and the curly brace on its own line for the opening closing curly brace. Functions are usually defined when we get to class member functions. The first letter is lowercase, and then it's snake case. Yeah, and line length is 79 characters because punch cards.
So, has everybody compiled gem5 again successfully? Please let people in the room know if you haven't. I'm going to give you guys like 3 minutes. Sorry, I kind of lost the second half of the question.
So, yeah, so you have multiple SimObjects in your description files, you have multiple source files for each of those SimObjects.
Yes.
So how does that change like the source file in
Oh, you just specify every .cc file, and basically in the SimObject list that we specified, put the name of everything.
So is it like one source line per source file, or is it just kind of?
Yeah, one source line per source file. Yes.
So yeah, you'll see soon. You'll add new source lines for each source file you want to compile, and then you add a SimObject line for each file that has SimObjects in it, and then a list of the SimObjects in that file. Great question.
Any other general questions?
Okay. You guys have, well, I'm going to give you another 90 seconds. Okay. So, I'm assuming that everybody has now compiled gem5 with the hello SimObject in the binary. So what I want you guys to do is open up. We're going to take a look at that magical file that we talked about. So what I want you guys to do is to go to gem5 build null params hello SimObject.hh. The path to this file should be on the slide 13. Okay. Remember when I said that gem5 makes sure that hello SimObject params is inheriting from SimObject params? So, voila. Here, you can see that this auto-generated code for the struct hello SimObject params is inheriting from SimObject params. So therefore, it is possible for you to pass any object of hello SimObject params to any function that takes SimObject params, i.e. the constructor of SimObject. Isn't that cool? Okay. Again, basically showing the same thing. Let's assume that we have a class hierarchy like this, where hello SimObject and clocked object inherit from SimObject, and base CPU inherits from clocked object. So you can draw a parallel between this inheritance hierarchy to the inheritance hierarchy for their respective params. So then hello SimObject params and clocked object params inherit from SimObject params, and then base CPU params inherits from clocked object params. Any questions?
What are params?
So all the parameters that we are going to add in the Python file are going to be compiled into a C++ struct that are passed to the constructor of your SimObject. So then you can like tune the different parameters of your SimObject. So this SimObject that we built does not have any parameters yet, but we're going to add parameters to it. But if you want a specific example, look at the size parameter for the cache SimObject. Remember, in the first 2 days, you changed the size of the cache to see the impact of a cache size on the performance. That size keyword was a parameter of the cache SimObject.
They're literally parameters in the traditional sense.
Yeah.
I was working both Python and C++, just kind of a code that makes sure that what you do in one works in the other. But
Yeah.
parameters for less complex.
Yeah. And we also just right now looked at the code for hello SimObject params in build null params hello SimObject.h. Okay. So now let's actually get to simulation. But before we do that, I want you guys to open up gem5 source bootcamp run_hello.py. Okay. So we call this script, let me actually open this up too. So we call this script a config script, which basically configures and starts the simulation for the computer system that we want to simulate. So with every config script, gem5 creates a SimObject tree that describes the connections between the different SimObjects in your system, in your computer system. And this computer system that we're going to build right now does not have a CPU, does not have a cache, does not have a memory. It only has one hardware, one piece of hardware. And that is a piece of hardware that just can say hello. And we will do that through first creating a root object. Root is a special SimObject that is going to be the root of that SimObject tree. So every object that you add to your config script is going to be added below the root SimObject. And we're going to add hello as a child of root. So if you draw an imaginary tree, there's going to be root at the top. And by saying root.hello, we're adding a child vertex to this tree that is of type hello SimObject. So gem5 knows how to instantiate different SimObject because the gem5 knows how to traverse this tree. Okay. And after that, we're going to make a call to m5.instantiate that actually traverses this tree and instantiates, i.e. calls the constructor for SimObjects in C++. And then after that, we're going to call m5.simulate that basically starts simulation. Okay. Okay, so what I want you guys to do is to run this command in green in the gem5 directory. And I'm going to do it with you guys. So feel free to copy and paste, but I suggest you don't. Clear and do build. Team. Okay. So I'm going to press enter, and we're going to see what's going to happen. Okay. So we can see that a hello world from a SimObject constructor in parentheses is printed. And I want you guys to pay attention to the order of printings. So if you open up the run hello py file, you can see that this hello world statement is printed before beginning simulation. So this, that line of code in here, this line, stdc out, was executed when you call m5.instantiate. Okay. Okay, so we have created a SimObject now. So as a developer or as a researcher, you're going to create SimObjects. And SimObjects are not going to be as simple as a hello SimObject. Like we have out-of-order CPUs that we model with SimObjects. And I'm like 99% sure that when you start building your own SimObject, you're going to run into compilation errors. You're going to run into functional errors, like correctness issues. So how do developers in gem5 debug their code? Gem5 has a really nice feature that facilitates printf-like debugging. And there you can enable different printfs by specifying different debug flags. So when you add a printf-like statement, you can specify only print this when this flag is enabled. And in order to add a debug flag, we can add a definition for it in any scan script. So let's go ahead and do that. Let's add a debug flag for our SimObject. I want you guys to open the same scan script from before and add this line, debug flag hello example flag. Make sure to get the spelling correctly because, make sure that you remember what name you give this debug flag. Because the way that we access this debug flag is through its name. So, okay. So what next? How do we use this? Okay. So there is a printf-like statement called dprintf, which lets you print debugging statements. And the way that you use it is just adding one extra argument to the printf function. That is the name of the debug flag, and then a formatted string along with the values that are going to replace the identifiers. So we're going to go ahead and replace that stdc out with a dprintf. So what I want you guys to do is open hello SimObject.cc. I'm sorry, this is incorrect. So this is hello SimObject.hh, but you guys should open hello SimObject.cc. Sure, this is, and let's open hello SimObject.cc. So let's get of the IO stream include first because we're not going to need it anymore. And let's instead include from the base directory in gem5 trace.hh. This file has the definition for the dprintf statement. Next, let's include another auto-generated file. So when you add a debug flag to a scan script, it's going to create a header file in debug, name of the debug flag, .hh. So this is an auto-generated file. I want to note that these auto-generated files are not going to be found in source. you can only find them in the build directory. So the same path relative to source, but follow that from null. Does that make sense? OK. So make sure to use hello example flag, because there already is a hello example in the gem5 code base, and we don't want these two flags to clash. OK. So now, let's comment out this stdc out, and let's add a dprintf statement. So let's just type dprintf and pass hello, hello, oh. Hello example flag as the flag that we want to use to enable this statement. And then just let's print the same thing. I'm going to just add a special string in the beginning of this hello world. I'm just going to add a colon and say hello world from a SimObject. And I'm not going to put the name of the function in parentheses anymore. And what I'm going to do next is specify what is that string that I want to put inside this formatted string, which I specify by passing underscore underscore func underscore underscore. And that's it. So this underscore underscore func underscore underscore is a special keyword that will return the name of the function that you're in. And since we're exceeding the line limit, let's not. So I'm going to break this in 2 halves and make it look a bit prettier. OK. Any questions?
If you think there's a little magic here, it's because there kind of is. There's a lot of auto-generated stuff. Classes being generated by the Scon script compiler. Let's be clear.
OK.
It is as magic as you think it is.
Yeah. OK. So we're not going to compile gem5 yet. We're going to add more interesting stuff to this SimObject. OK. So as you remember, Jason talked about gem5 being a discrete event simulator. So there are 2 things that are special about gem5. So it has discrete time, and it's event-driven. So events, if I want to give you a high-level understanding of them, are means for you to make function calls in future. So the simulator is going to move time, and you can tell the simulator through events when in the simulator time to call specific functions. That is not the only thing that events do, but that is one of the main things that they do. And gem5 has a priority queue, and events are going to be inserted in the queue, sorted by the time they are scheduled for. For example, and the way gem5 does the simulation is that it pops one event from the event queue. So the first event from the event queue is popped. Then that event will tell the simulator what function to call. The event is executed through calling that function. And then that event might schedule another event. Or that function might schedule or add another event to this event queue. So now, for example, event 10 is popped. It's executed. It adds event. An event at tick 55. And then event 11 is executed, and it wants to add an event at tick 51. So since this is a priority queue, this event will go and sit right here. So it's not going to go to the back of the queue. Any questions? OK. So all SimObjects have facilities to enqueue events into this event queue. And so I want to add this note that might be a little confusing. So when an event is popped and it's executed, so it basically calls a function, that might schedule the same kind of event in the future. So this is a possibility. And that's actually what we're going to do. OK, just another example of how you do reads. I think Jason went through this with you, guys. So for example, when there is a request to the memory put in the read queue of the memory controller, an event is scheduled to read that request at a later time. And then other things happen, and the data is read and sent to the processor. So now let's go ahead and actually add an event to our hello SimObject. OK, so what I want you guys to do is to open hello SimObject.hh again. OK, so there are many ways that you can add an event to your SimObject. But what we're going to use right now is through event function wrapper. So it wraps the function that the event needs to call along with the event into one simple object or pointer. So I'm going to type event function wrapper, and I'm going to name it event. And I'm also going to specify the function that this event is going to execute when it's popped. And let's call that process event. And one thing to note here that these functions should not return anything. So they are all void functions. OK, I'm going to give you guys how many? 30 seconds to add these two lines. OK.
After waiting for that, anybody else? It's been a couple days since we talked about linear simulation. Any questions about that? And start to settle in your brain. Things still make sense. Yeah.
How to decide if you're just doing like normal like O3 operations, right? And you like use an event for like some table to just like clear the ROM, right? Can you just like do anything at any point?
Yeah. You can do anything at any point. But yeah, you have to be really careful in designing your model to make sure you do things that make sense and also do things that don't break things.
Yeah, it seems like I'm sometimes like follow like execution of like 1 and 3. It seems like there's no viable path to do what you want, right? There's no place like how to just queue it up and it'll just jump to the side, perform some operation, come back.
And that particular tick, it will execute that function. So it's not a, when you're running in timing mode, there isn't much imperative code being executed. It's all asynchronous. Or maybe there's a mix because each asynchronous event it is an imperative code.
OK. So we now have added an event definition to our SimObject. But how do we add that event to that event queue? Or when do we add that event to an event queue? So if you guys go ahead and look at the SimObject.hh file, you guys just can trust me here. That SimObject class has a virtual function called startup. And it's one of a few special functions that are called when you call m5.instantiate or m5.simulate. So this startup is called right after m5.simulate is called. And at this point, when startup is called, every SimObject in the computer system that you're describing with your config script is instantiated. All the ports are connected so every all the SimObjects can talk together to each other. And if your SimObject needs to have an initialization or an initial event to kick things off. This is the right place to do it. So this is at tick 0. This is called at tick 0. And you can schedule things, kick things off. For example, your CPU probably would be the place to schedule an event which starts reading instructions from the memory and executing them. So this is the place to schedule initial events, right? We want to keep scheduling events so that we can separate function calls over time. Does that make sense? Any questions? Great. So now let's go ahead and add the definition for that function. So it is a public function because the simulator needs to call this on every SimObject. So let's just say virtual void startup override. This is it. OK. OK. I'm going to give you guys like a few seconds to do that. OK. So now, sorry, go ahead. So these are like directives to the compiler that are saying that we're overriding this virtual function. So SimObject has this startup function. So this is a function that hello SimObject is inheriting from SimObject. And we're going to override the implementation of SimObject. That is what we're telling the compiler. I think you would be fine if you don't put override there, but it's a nice thing to put there, and I recommend putting it there. Sorry. Go. Multiple startup. So your SimObject only has one startup, but yeah. So when you call m5.simulate, it's going to call m_startup. But no, not necessarily. Like there's a default implementation for it in SimObject, but you can choose to override it. But when you call m5.simulate, it's going to go through that tree again and call startup for every SimObject in your system. Does that make sense? You have it. OK, great. OK, so now we have added the definitions. Let's go ahead and initialize and implement things. OK, so we added a private member to this class called event. Let's go ahead and initialize it through the initialization list. So event function wrapper takes 2 arguments to instantiate an object. The first one is a function that will be called when the event is being popped from the event queue. So we can express that function through lambda expressions here, and that's what we're going to do. So we're going to say capture this, the whole scope of the SimObject, and in that scope, we're going to call process event. So basically, what this first few characters say is that whenever you pop up an event of, well, this event, call process event from hello SimObject. And the second thing that it needs is a name. Let's give it a name. So SimObject conveniently has a function called name, which returns the name of the SimObject. And also, let's just add a dot event to the name.
By the way, this name is the name for this particular instance of hello SimObject.
Yeah.
So if you make 5 different hello SimObjects in your Python script, called like hello1, hello2, hello3, that name will return hello1, hello2, or hello3.
Yeah. OK, so we added 2 functions to this class. Let's now implement them. Let's first go ahead and implement startup. So it was a void hello SimObject ::startup. And again, as Jason said, the style is that when you're implementing a function, you put the braces one line after the prototype of the function. So you shouldn't, so according to gem5 style, you shouldn't define functions like this. This brace should go to the next line. Yeah. Okay. Sorry, can you? Okay. So what we're doing here is that we're initializing that member of the class hello SimObject that was called event, right? Let's go back to hello SimObject.hh and see. So it was a member of the SimObject of the type event function wrapper. And the constructor for event function wrapper takes 2 arguments. One function that we're implementing through lambda expression here. So this piece of code is telling the simulator to call process event from hello SimObject. But we're capturing this and calling process event from this. Does that make sense? Okay. And the next thing is just giving it a name. Okay. So now any other questions? Okay. Let's go ahead and implement the startup. So we now have added debug flags, so we're going to be very liberal with them. So let's do a dprintf, hello example flag. And let's just, again, do hello world, or from a SimObject. I'm assuming this will run over. Yes. OK. OK. So the reason that I'm adding the name of these functions to the debug statement is for you guys to see the order of function calls. So we're going to see the constructor being called first and then startup. And this debug statement is going to say probably root.hello.startup, something like that. And now, since we talked about startup being the appropriate place to schedule initial events, let's schedule an initial event. Before we do that, there are other initialization functions here that are specific to how you run the simulation. So init is the first initialization call. Basically, it initializes parts of your SimObject that don't rely on unserialization. After that, there's init state, which is only called where you're starting simulation fresh. So when you're, for example, this function is not called when you're restoring your simulation from a checkpoint. And you'll see how you do that on Friday. And there's load state, which is actually called when you're storing your simulation from a checkpoint. So these functions might be called at different times depending on what you're doing. These 2 functions, init state and load state. You can read more about them in our doxygen, which I think is still broken. But you can read about that on SimObject.hh. There's a huge documentation. OK. Oh, OK. OK. So let's see how we can add events to the event queue of the simulator. So there's a function called schedule that is part of event manager. And SimObject itself inherits from an event manager. So every SimObject is an event manager. An event manager has a function called schedule that takes 2 arguments, a pointer to an event, and a tick at which the event should be scheduled at. So you can communicate to the simulator that I want to schedule some event at some specific tick. I want you guys to have this in mind, that the tick that you pass to schedule should be expressed in the global sense, or in the global simulator time. So we're going to have a few function calls that gem5 provides us to be able to describe what we have in mind relative to some absolute time that gem5 gives us. But now let's go back to startup function and schedule the event for tick 100. So what I'm going to do is just call schedule. And since event from the hello SimObject class is a pointer to an event, so event function wrapper is also a pointer to an event. And I'm going to schedule that for tick 100. So let's create a mental picture of what's going to happen. The constructor is going to be called, and after that, the startup function is going to be called, which will enqueue an event of the type event, or an event at tick 100. And when simulator looks at the event queue, there's going to be an event scheduled for tick 100. So simulator will move the time to tick 100 and then call the function that this event is pointing to, which was, I want one person to answer this. Process event, exactly. So let's go ahead and implement that function. So again, void hello SimObject process event. OK. Sorry, I'm going to scroll this up for everybody to be able to see. And again, let's use a debug print. Again, hello world. Oh. Yeah. Sorry, Jason, what? Outside what? Codes. OK. So what we did was say hello once in the constructor, say hello another time in the startup, schedule an event for tick 100 in the startup, and say hello again when we're processing that event. OK? So again, creating a mental picture of what's going to happen before we see that happen. Tick 0, constructor is going to be called. Tick 0, startup is going to be called. And at tick 100, process event will be executed. OK. Now let's compile things. Let's compile null again.
So are those events different from, like, say, the exit events? Like,
So exit events are also events. They're like,
also, are we creating our own events then?
yeah. We're actually going to add, like, schedule an exit event through some of the function calls that. Through the functions that gem5 provides. Like gem5 has a few function calls that allow you to schedule exit events so that you can get out of simulation and return control back to Python. Oh. Okay, great. Thank you. Any questions while this is compiling?
Are you going to do an event, schedule from an event? Or are you going to
Yeah,
move on to the next thing now?
I'm gonna have so I'm gonna give it like 5-minute break, and then we're gonna.
That's what I was going to suggest.
Okay. I think I'm way off on my estimation. Okay. Do you have a question? Okay. Can people in the room help people get compilation done? Okay. Has anybody completed the compilation successfully? Great, great, good job. I'm going to wait another minute. Another 2 minutes. So have you been able to? Yeah. Yeah. Let's see. Oh, you're missing a comma here.
Myra, I think this goes to your question. I think maybe worth clarifying. The 100 you specify there, is that the absolute 100 tick or 100 from when you schedule that event?
That's the absolute 100th tick. So this is saying schedule this event for tick 100. Also, you have to remember that you cannot schedule things for past. So if you're at tick 200, you cannot schedule things for tick 100. Yeah, we're going to see that. Yeah, yeah. We're going to see those actions later on. Okay. No. Yeah. No, not yet, but we're going to cover it. We're going to cover it later. We're going to modify. Yeah, yeah. So, yeah. Yeah. So you guys are going to see how we can schedule things for relative time instead of absolute time. Okay. So what I want you guys to do is to, again, run hello with gem5. So copy and paste the first command from this slide, slide 27, into your terminal, or you can type it. I recommend typing in case I've made a typo when typing. Okay. Okay. So let's run this. Run hello with gem5 again. Okay. We see that all the hello worlds that we printed out in our code are not there. And this is the magic of dprintfs. Now I can enable printing those from outside the C++ code. What I want you to do now is to run the second command on slide 27. So what we're going to tell gem5 to do is to say gem5 to run with this debug flag enabled. So we're going to pass a list of debug flags that we want to be enabled. And remember, we created a hello example flag. So what this command is saying, run gem5, enable hello example flag, and use this script to simulate. So remember, we didn't see all those hello world. Now they're going to appear here. OK. Great. So if you look at the print statement, you can see first, hello SimObject, or the constructor of the class, has been called to say hello world. After that, the startup function has been called to say hello world. And you can see there's something different about the third hello world. And that is the number that the line starts with. All the other print statements have a 0, which specify that these things happened at tick 0. But since we scheduled event for tick 100, this print statement that comes from the process event function is going to be printed at tick 100. Any questions? Uh-huh. OK, so that's a really good question. So gem5, when it reaches the end of that event queue, and there is no event left in the event queue, it's going to fast forward time to max tick, which is 2 to the power of 64 minus 1. So this is why you see that we exited simulation at this very huge number tick. And this is not, like, the model that we developed right now is not still useful, because if we start simulating things like this, everything takes max tick time. So now we have to figure out to exit simulation and tell gem5 to exit simulation before fast forwarding time to max tick. So are there any other questions? If there are not any other questions, let's take a break, have some coffee, orange juice, or pastries. Yeah, 10:30.
And anybody has questions, just raise your hand.
Yeah.
What happens if you schedule 2 events in the same tick?
Oh, so they will be both executed at the same tick, but I think there's an arbitrary order,
Yeah.
so you should not depend on one event happening before another event. Yeah. SimObject, more interesting. Okay. Is everybody ready to start programming? Okay. Okay. So before we start programming, since everybody's not ready, I want to ask everyone to see if you observed the things that I expected you to observe. So between these two commands, we enabled hello example flag, which kicked off printing those print statements. I want you guys to observe the output difference between these two commands, and I'm hopeful that you guys did observe this. So when you enable the debug flag, those print statements are there. If you don't, they're not there. Another thing that I wanted you guys to observe was that max tick, that very huge number that gem5 reported that the simulation was over. OK, so we're going to fix that max tick thing in this section of the tutorial. So let's go ahead and do that.
But first, do you have any, like, what sorts of things might be wrong if it's compiling without errors, but adding a code flag doesn't show it? Have an instinct?
Well, an easy answer to your question would be functionality. Like, you might be modeling a cache, but not scheduling events correctly so that the timing is not correct.
I'll answer differently. It's other type.
Not the compiler.
Yeah, it's like a type of a debug flag.
Oh, OK. So this was not a general question. Yeah. 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 So one possible typo would be typing hello example instead of hello example flag, because the autocomplete will offer hello example, but not hello example flag. So make sure to use hello example flag in your dprintfs, or pass hello example as the flag that you want, I guess. OK, so let's make this a little bit more interesting, by which I mean let's make it say hello more than one time when it's processing event. So let's schedule more than one event. So what we want to do here is to be able to say or print out the statement, hello world processing the event n times every L ticks. So 2 parameters. We want this to print it n times every L ticks. So let's go ahead and do that. So I want you guys to open up hello SimObject.hh, and in the private section of your class, I want you to add a member of the class of the type tick. So if you type capital T I C K, it's a type defined by gem5, and let's call that latency. Let's add another member to this class, which is of type integer, and let's call that times left. OK, great. So now we have added those 2 parameters that we want to be able to change to our C++ implementation. Now let's change process event to account for this change. What I want you guys to do is open hello SimObject.cc, and let's go over how we can change this so that we print this statement as many times as specified by times left. So, OK. First, I'm going to comment this because I might want to copy it later. But let's say if times left bigger than 0. So if we still have hello statements to print, first let's decrement times left. So, and then let's add a print statement to say that hello. Again, it's a dprintf, so let's pass hello example flag. And then, again, name of the function, processing an event. Also, right now, let's specify how many hellos are left to say. I'm going to say %d greets left. And I'm going to add a new line and print name of the function and times left. OK. So if we still have greeting to do, we're going to do it. We're just going to print it. OK. So now, remember that max tick issue that we had? Let's solve that. So now if times left has reached 0, and this is like another gem5 style guideline, when you're writing if statement, you can choose to both put the braces after the parentheses or add a new line and put the braces. But you have to make sure there's a space between the parentheses and your brace. So if times left is equal to 0, which basically means that we have said hello as many times as we were supposed to, let's say that we don't have anything left to do. Hello example flag. And let's just say, again, done greeting. And just specify the name of the function because we like it. OK, so since we're done greeting, from the perspective of this hello SimObject, simulation should be over, right? We should now tell the simulator to exit simulation. OK. So I'm going to use a function that gem5 provides, and it's defined here. I'm going to add include sim/simexit.sh. So this file defines a few functions that let you exit simulation with different types of inputs that you give them. So there's a very clear function, very self-explanatory, exit simloop now, which only needs one argument, one mandatory argument, which is the message that you want to communicate to Python. So when you call this function, it's going to schedule an exit event, which is going to return control back to Python. And with that, it's going to also communicate this message that you put here. Let's just say no greets left. So by adding this line, we're telling gem5 we want to exit simulation right now. So do that for us, please. OK. So if I were to compile this right now and run hello, do you guys think this will be printed as many times as times left? No, because we have scheduled one event for tick 100. That event calls process event. That process event does something, but does not schedule anything if it doesn't schedule the exit event. So now let's do the scheduling again. So we're going to say if times left is bigger than 0. So if we still have hellos to say, let's schedule an event for saying hello. So let's call schedule. So remember when I said an event, the function that processes an event can schedule the same event in the future? Now let's do that. So let's schedule the same event for future, right? So we said we want this to print this statement as many times as there are times left. And we want the prints to be latency ticks apart. So as I mentioned already, schedule takes an absolute tick. But latency is a relative term. So what we need to do to get the absolute tick from latency is using curTick, which is a function that gem5 conveniently implements. So this function is going to return the tick at which this function is called. So we're going to schedule event for current tick plus latency tick. Is this clear? Or are there any questions? Oh, so we're going to get to that later. We're still not done. Sorry. Which one? I'm sorry, I can't hear.
I think I understand the question. I think the question is, why do you have 3 if statements if you could have done it in an if else?
Okay. I mean, this is more readable to me. Yeah. And, well, I learned this the hard way, but writing very readable code helps when it comes to developing for gem5.
You realize it is never going to reach the second if statement. The third one. Yeah.
Why would it?
No, sorry.
Schedule on it versus.
Okay. So we're going to see what happens next. So, okay. So before we initialize latency and times left, let's go ahead and change something else. So we were at tick 0, and we wanted the print statements to be printed every latency ticks. So let's change this 100 number to latency. Okay? So again, let's create a mental image. Constructor is called, then startup is called, which schedules an event for latency ticks. And every time that process event is called, it's going to schedule the event for latency ticks from now. Does that make sense? Is that clear? Are there any questions? OK. So now we have 2 things to initialize. Latency and times left. So
Can I suggest jumping straight into the parameters for this instead of jump?
oh, yeah. OK. So I want to ask a question. So if I were to just hard code values in this, initialize latency and times left, would this be a useful model for me? Because every time I want to change these values, I have to recompile gem5. And actually, this is kind of counterintuitive to what SimObjects are designed. So we want times left and latency be tunable outside the C++ realm. And we're going to do that by adding parameters to our model. So in order to do that, first, let's ask if it's possible. Yes. Gem5 allows you to add parameters to your model from the params package. So what I want you guys to do is to open hello SimObject.py again. So let's add a line that says from m5.params import star. So what this line is saying is that, so we know that gem5 implements a few different types of parameters that you can add to your SimObjects. Let's import all of them because we don't know specifically what we want. OK. So the way that you specify a param in your SimObject is basically by first giving it a name. Let's give latency another name, just so that it's clear that names don't have to be the same. So let's just call this time to wait equals to. And then param, we're going to use this param that we imported from m5.param. And give it the type latency. OK. OK. What this line is saying is that I have a parameter for this SimObject is of type latency. And again, this is a Python-like language. So gem5 has a specialized interpreter that understands this. Don't think of this as classes in Python. These are gem5-specific lines. OK. So what do we need to pass to the constructor of this parameter? So every parameter at least needs one mandatory argument, which is the description for it. And let's give it a description, time to wait before greeting. OK. Okay. Now let's add another parameter, which is going to be our times left. Let's give it the name number of greets, which is an integer parameter. So I'm just going to say param.int. So another way that you can add a parameter is by specifying a default value and a description. So let's just give this number of greets a default value of 1, and let's give it a description. Okay, so what I want to mention and caution you about is to never instantiate a SimObject as a parameter for your, for the default for a parameter. So what gem5 allows is to specify SimObjects as parameters to another SimObject. This is confusing. I already see it in your face, but just trust me that you can do to specify SimObjects as parameters for other SimObjects, and you should never instantiate a SimObject inside this parameter definition. So if you want to set one parameter that is SimObject to another SimObject, you should do that from your config script. Never, ever call the constructor of a SimObject when you specify the default value of a parameter that is a SimObject. OK, great. Again, let's trust the magic that gem5 does and go back to our CC function, CC file. So let's trust that when I recompile this params object is going to have a member called time2wait, because that is what I specified I need in my params object in Python. And let's also trust that it also has a number of greets. OK. Now we have successfully communicated parameters from Python to C++. Therefore, every time we want to change that parameter, we don't have to recompile gem5. So we're getting close to the point where we can model things. And we can actually now start changing the behavior of this hello SimObject by passing different numbers to it. OK. So let's see what are on the slides. Yes. So let's go ahead and recompile gem5. And here. OK. I'm going to give you guys 3 minutes to catch up with the code on compilation.
Can you pass a more advanced data structure than strings and ends? You can also pass instances of other SimObjects. And there's also some special params that I already talked about in a few minutes, which are ports, which are a more complex data structure that set things up in the background when you're using it. Just to reiterate something Mayar said, in the SimObject description file here, where you're specifying your parameters, this is Python, so you could do anything in Python in here, but it's executed during the build system. So if you use just Python code, sometimes you can get really weird results. code to be in your in the Python. That's where you use like the standard library and extend the SimObject to the Python.
Okay. So I'm assuming everybody has, do you have a question or do you need help? Okay. Do you have a question? Okay, you need help?
It says exit sim loop now is not declared.
Did you include the header file for it? Oh yeah, so sim exit include sim/sim underscore exit.
Got it. Thank you.
No problem. Okay, so before we run this, I want people to try to predict what's going to happen if we just run the same command that we have been using. Do you guys think this is going to run? No? So why is that? Sorry. Yeah. So which parameter specifically? Yes, exactly. So since we haven't defined latency, well, we haven't specified a specific value for latency in our config script, it's going to complain that, well, I don't know what value to set latency to. So let's go ahead and do that. So you can simply do that, but when you call the constructor of this SimObject. So let's do time. So, and we're going to see cool things about params here. Very human readable things. Time to wait. Okay, so now we don't have to express things as ticks anymore. Let's just say 5 nanoseconds. And gem5 knows how to convert this properly to the thing that C++ expects because you set correct type of parameter in your Python, and you also added a correct type of member in your C++ class that corresponds with latency. We had tick that corresponds with latency that we use to define parameter time to wait. So what gem5 is going to do is take this 5 nanosecond string, convert it based on the type of the parameter that it is, which is latency, and convert it to a number that C++ understands. And now let's also change the number of greets to 15. Of greets to 15. Does someone want to tell me what's going to happen? Like what print statements we should be expecting? So before we run this, can you predict what's going to be printed on the terminal when we run the simulation again? Yes. So just to confirm, we're going to still see print statements from constructor and startup, but now we're going to see 15 hello worlds, and then 1 done greeting. And then we're going to also see that simulation does not end at max tick. It's going to end at a different tick. So this is what we expect to see, and we hope to see that is what's going to happen. So let's run the simulation again. Again, let's specify the debug flags and see what happens. OK, confirming what we expected. At tick 0, constructor and startup print statements. And so 5 nanosecond is 5,000 ticks. So at tick 5,000, we see hello world, or well, processing an event. And it says, well, I have 14 greets to do. And then goes on until it runs out of greets. It tells us that there are no greets left. And you can see that simulation exited at tick 75,000 instead of that very huge number. And you can also see that because no greets left is printed here, which was the same string that we passed to exit sim loop now in our C++ implementation.
If I change anything in the CC file, do I have to recompile gem5?
Yes. if you make any change to C++ code, you have to recompile gem5.
Yeah, I had a question from the audience. I didn't know the answer. Is there any way to avoid scheduling things the same way?
So this is a very tricky question, but you should never schedule the exact point, the event, twice. So there should never be two, like gem5 will complain to you if you enqueue to this exact event twice in the event queue. So that's one part of it. So gem5 will complain to you if you do that. So that's
It's not about the same event. It's about two events having executing the same tape.
okay.
Is there a way to avoid that? And what are the
Yeah. So
that
yeah.
events are processed?
Yeah, so for example, events have a function called, so for example, we can see if this event, named event, has a function called schedule. Okay. So this returns a Boolean. So if you call this an event, sorry, there's no.
About that event being scheduled, the question was if you have two events at the same tape, it could be two different events, right?
Uh-huh.
How do you stop that from happening?
Well,
You can't. Is there a policy?
so that is possible if the two events know about, like if you know what two specific events should not happen at the same take. So when I'm scheduling an event, I will check here for.
So when you're implementing your event, you just have to have some rules in place.
So you have to implement those rules. For example, let's say I had an evil event. I will check it here if evil event dot scheduled. Well, I will only schedule this if evil event is not scheduled.
I guess that's a way to do it.
Yeah. Does that answer the question? Well, Jason had a smart answer for it.
Related to this question, let's say like memory response is like coming, and it should be exactly timed at like 100.
Uh-huh.
But then another memory response is supposed to be timed at 100 also.
Uh-huh.
Then,
When I guess then you're modeling your memory incorrectly.
or if you have like both the same memories that has the 100,
Uh-huh.
it should return at 100.
Yeah.
But if we
Yeah.
deliberately delete to 101, that is inaccurate. So like,
Yeah, but so like if you're talking about having two instances of memory, you're going to have two instances of that event. So it's not the exact same event, right? Every SimObject is going to have, like every memory SimObject is going to have its instance of event.
but don't you have like just one queue?
Yeah, but those events are not the same event.
Won't there be like race conditions or other?
Sorry, 1 second. Let's use some more precise language.
Yeah.
So you cannot schedule the same instance of an event at the same time. So if you say new event, whatever, new event, my cool event, new event, my other event, those two events can be scheduled at the same time. But my cool event can't be scheduled for two different things. Does that make sense?
Yeah, I understand that. But then I was wondering that if you have two different memory events coming at the same time,
So,
that's valid, but then what happens?
electronics are parallel. So it's like if you have two wires pulled high at the same time, what happens? Your logic has to deal with those two wires being pulled high at the same time.
Well, so you have to also implement that logic stack.
Yep. So for instance, if you have a port coming in, and you can only accept one thing per cycle, you have to reject. And if two things show up at the same time, you have to reject one of them. And you have to have some kind of logic to make sure that works. And that's about the modeling of the system. So for those of you who are having the error about exit sim now, you need to include simexit.sh.
Okay.
Can you go back to the evil event that you just added?
Uh-huh.
So that will prevent two events from executing at the same time, right?
Sorry.
That
Well, yeah, that prevents evil event and event being scheduled at the same tick. Well, no, not even at the same tick. Being scheduled at, being in the queue at the same time.
So where's that defined?
Oh, so this was a hypothetical situation where we had another event. Like your SimObject can have more than one event. So this is something that you have to have in mind, right? For example, a cache, like one way of designing a cache is to have an event that checks for the tag and index, have an event for creating like memory packets to send to the memory if it's a miss. Sorry.
Yeah, to speak to what you're saying, I think, I forget where it is exactly. I think it might be in like memory interface. But you can, I think in there, there's, I don't remember if I'm looking at somebody else's code or if it's in there, but like you can use a flag to say like, oh, this event has finished. And so you can check that flag, like, okay,
Yeah.
let's say you're waiting for some memory event to finish before you can schedule the other one. And in your function that's trying to schedule this event, you can check this flag, and if this flag is not flipped yet, you reject the event, you say, okay, try again on the next tick. And then you keep doing that. You basically cycle there until the flag is flipped, and then you finally schedule that event.
Yeah.
So if you're like limiting it, it's like a lock. So there is a way to do it.
Yeah.
Not very complicated, just using a flag.
Okay. Okay. So for those of you who want a completed version of this, if you go to the completed directory, there's the completed code already there, and you can use that to get things to compile. And there's a typo in the name of SimObject. It says SimObject. Make sure to fix it before using it, and also make sure to complete the scan script because the scan script is not provided as complete. Okay. Okay. So before we continue, I want you guys to try to compile gem5 for x86. Please use this command to compile gem5 with x86. I'm going to give you guys 2 minutes to get this command going, and we're going to start talking about how we interact with memory. Am I going too fast?
I think you're doing really good.
Okay, great. Is everybody compiling gem5 for x86? Okay. 5 seconds. Okay. So let's start creating a little bit more complicated SimObject. This SimObject is actually going to interact with the memory. So this is one one very interesting part of gem5, and it's really important that our SimObjects can do that. So the task at hand is to design a SimObject that sits between the CPU and the memory. What it does is just basically forward the requests from CPU to memory and responses from memory to CPU, one packet at a time. And it also has separate interfaces for instruction and data because CPU also has separate interface for instruction and data. So one side of this SimObject will be connected to a CPU, and one side will be connected to a memory. So we're going to prime this so that it can connect to both. So I talked about I'm going to talk about this thing called packet, and we're going to see what it is. So packet is basically an encapsulation of all the information that you need to be able to communicate and interact with memory. It has header fields like memory command. It could be read request, write request, read response, write response. It has a requester ID, which specifies what SimObject was that created this packet, what SimObject was that is requesting something. It's going to have an address. Basically, with every packet, you're going to access an address in the memory, which is specified by address. And depending on what memory command you're using, it's going to have data. So for example, read requests don't have any data, but read responses do. Or write requests do have data, but write responses don't. OK. So I want you to also grasp this request and response terminology, because this is what we're going to use very often. OK. So this is the high-level overview of what we're going to design. We're going to create a simple memory object. We're going to call it simple memObject. It takes a packet that, for example, is read request. It doesn't have any data. It's going to simply forward that packet to the memory. And then when memory has that data that packet A specifies ready, it will send that data back to simple memory object. Simple memory object is then again going to simply forward that packet to the CPU. Any questions?
Sorry, how about the x86? Are we supposed to see anything different?
No, not yet. OK, any other questions? OK, so you saw that a packet is moving throughout the system, and the things that are facilitating this are called ports. You've been hearing this name port throughout these days, and this is the first time that we actually tell you guys what they are. So basically, all the memory objects in Gem5 are connected to each other through ports. So ports are of two types, request and response. And there are three modes of memory accesses. I think Ayaz has already talked about them. Timing is the only mode of memory access that results in correct simulation results of memory accesses. It's basically going to move time with every process that happens in the memory subsystem. And this is what we are going to be focusing on. Atomic basically accesses memory through a long chain of function calls. So every memory access happens in the cycle. So it's in Gem5, atomic mode is used for fast forwarding. And there's another mode of access which is functional, which mostly is used for debugging purposes or kind of implementing hacks. And it's also useful for communicating from host machine to the guest machine. Any questions? OK. So I talked about request and response. And these are the two types of ports that we have. You're going to see counterpart functions between the two port classes. These are the objects that facilitate data movement. Request and response port have various, like these three special functions that move the data around. Request port has send timing request and receive timing response. So request port sends a request and receives the response. On the contrary, a response port receives a response. Receives a request and sends a response. And in case that any of these ports don't have the receiving bandwidth, there's a retry request process. So receive retry request is a function that allows for the request port to receive a retry from response. So for example, if at some point response does not have the bandwidth to receive a request from a request port, in the future, it will send it a retry when it has the bandwidth. The same thing could be said about responses. When the request port doesn't have the bandwidth to receive the response, it will tell the response port to wait for future when it has the bandwidth to receive it. One thing that I want you guys to pay very careful attention to is that in gem5 you can only connect ports of different type to each other. So you can never connect a request port to another request port. It should be always a request port connected to a response port. So how does that connection happen? So again, there's a lot of parallels between Python and C++ in gem5. Again, in Python, you connect two ports using the assignment or the equal sign, and PyBind takes care of making sure that the C++ implementation of ports have pointers to each other. So those pointers, let's call them, every request port has a peer that is a response port, that is a pointer to a response port, and every response port has a pointer called peer that is a pointer to a request port. Any questions? Do you have a question? Okay, so now let's look at 3 possible scenarios that might happen when these 2 types of ports are interacting with each other. Okay, so the most simple and easy scenario is that request port calls send timing request, which in turn will call receive timing request on its peer. So because request has a pointer to the response port it is connected to, it can simply, when you call send timing request, call receive timing request on that port. So if the response port or if the responder has the bandwidth to receive that request, it will return true so that the requester knows that the request has been successfully communicated to the responder. And responder will take some time to execute and prepare the response, which in turn will call send timing response on the response port, which in turn will call receive timing response on the request port. Again, if the requester now has the bandwidth to receive that response, it will return true, which basically tells the responder that this response has been successfully communicated to the requester. Okay, a little bit more complicated situation is where the responder doesn't have the bandwidth. Again, send timing request calls receive timing request. Responder is busy, so it returns false. Requester knows, well, I failed to communicate that request. However, responder knows that in future, when it has the bandwidth to receive it, it has to call send request retry, which in turn will call receive request retry on the request port, which tells the requester to now send the request again. And the same process will happen that we saw in the last slide, and the response is communicated to the requester. Another possible scenario is where the requester is busy, so the responder accepts the request, prepares the response. However, the requester does not have the bandwidth to receive that response, so it returns false. But in future, it will remember to tell the response port to send that response again, to try to send that response again. So this is not really, well, this is not really a common situation because the requester should, before making a request, allocate bandwidth for receiving the response of that request. But as you can see, there are places that this might happen, and it's useful to have. Yeah.
This protocol is a little bit complex. So why don't we sit with it for a minute and see?
Yeah. Oh, yeah. And by the way, there's a 4th scenario where both of them reject it first and send retries. But you guys can figure that out.
Okay, let me ask you a question. Let's say the sender is an L1 cache, the receiver is an L2 cache. So the requester is an L1, the responder is an L2. How would you add latency on the link between these 2 caches? So say you want a model that takes 5 cycles or 3 nanoseconds. Yeah.
Would you just have the responder just like
We just talked about the answer.
Exactly. So when the requester calls send-timing request, there's a set of functions, so imperative code, that is then eventually calls receive timing request. So that will be happening in the same test. So then if you want to model latency in your receive timing request, you need to schedule an event for the amount of latency that you care about for the future, and then handle the request at that point. Now, in your model, you can kind of choose either side here to add that latency, but you kind of need to be consistent across the model. Most things in gem5,
I think delegate the latency to the
it
responder.
depends on the model which
Yeah.
side the latency is.
Yeah. But from personal experience, it's very useful to have your design be consistent, at least with your own style, because then it makes understanding the model easier. Yeah, so like, yeah. So like that responder, when it executes, it takes some time, and you have to model that latency.
So the request port would schedule an event to send a timing request.
The SimObject that owns the request port would schedule an event to send a request. And then when that event executes, you would call the function send-timing request.
Yeah. So
Or you could do it the opposite way, and then call send-timing request when you want to send it, and on the SimObject that owns the response port would schedule an event to handle the response.
Gotcha. Okay. And then, okay.
And we'll see that
To
way.
handle the response where when it gets a receive timing request, then it schedules a set timing response event in the future where we then send
It schedules an event that will call that function.
yeah.
Yeah.
So what I,
They're trying to be quite precise.
yeah. So I think, okay, so. Yeah.
Okay, so this is a really good question. So if a port returns false and says, I cannot accept this request right now, it is the responsibility of that port to at some point in the future call retry.
Retry.
So either send request retry or send response retry.
Yeah.
It is, if that port does not do it, could be a deadlock. So if you return false, you must at some point call retry. Now, similarly, if request a response and you get false as the return, it is the responsibility of whoever received that false to track that packet. So they have to keep a pointer around that packet, they own that packet to make sure to send it. I guess the last thing is you can keep retrying, like you can keep sending it as much as you want and get that negative acknowledgement that you have as well. Again, when you're designing your own system in memory, you can kind of decide exactly what it's going to say. Yeah.
A reason why it might return if like an event is scheduled at that thing.
You're right. Yeah. So an example of why you might return false, maybe if the response port is an L2 cache, and that L2 cache only has a single port to the tags. So that means in a single cycle, it can only accept one request. In that ticket, it's already accepted a request, and then someone tries to send another request in that same tick. You might say, nope, I am already using all my resources. I cannot accept that new request. So it's a way to model the memory in different components.
Then usually don't you have to check before sending?
So in gem5's protocol, it is not a 4-phase protocol, it's a 2-phase protocol. You do not have to check before sending. That's why we have this complication of who owns what and when you have to do things. There is the option to use the 4-phase protocol like TLO. There is a try-send timing, which will tell you whether or not they can accept it, but most objects do not implement try-send timing.
Okay, so now let's go ahead and see how we add ports to a model. We learned how we can add parameters to a model or a SimObject, but we didn't look at how we can add connections or ports. So again, now what I want you guys to do is to look at this file. Oh, sorry. This file. And we're going to take a look at it and see what's going on. Okay. Okay, so the type response port and request port that you can see in lines 36, 37, and 38 are all defined, again, under m5.params. So if you want to import those, at least from params, the same kind of definition goes on for simple memory object that we're going to implement. CXX class, CXX header now point to a different file in a class, but the most important thing here is drawing parallels between what we wanted to design and what we added here. So we wanted two ports that connect to the CPU, one for instructions, one for data. And you can see that we have added an instruction port as response ports. So a CPU by nature is a requester. So it issues requests to the memory, which means that the receiving side should be a response port. And then let's add a port to be able to communicate with the memory, which we will call memport, which is of the type request port. So in order for our SimObject to forward things, it will take requests from response port and forward them to the request port. Right? Everything from inst port and data port will be forwarded to memport. Okay. And we said that we want this object to do everything one packet at a time. So one request at a time, we're going to do that. Okay. Now, let's take a look at this file, the .hh file for the SimObject, which you can see is already, there are still quite a few functions that we need to implement. And I want to ask you guys to believe me most of the time because we don't have enough time. Okay, so first of all, let's see what things we are including here. We're adding the header file for the definition of ports in the gem5 C++ code base. So that is in mem/port.hh. We're again including the parameters of this SimObject and also the SimObject header file. Again, gem5 namespace. One interesting part here is, so we're going to define a CPU side port class that inherits from response port. Again, let's go back to that diagram that we had in mind. We're going to respond to the CPU, so we want response ports to connect to the CPU. So we're going to create a class called CPU side port that inherits from response port. And let's keep a pointer to the simple memory object that owns this port. So in the private section of this class, we're going to keep a pointer of the simple memory object that owns this. We're going to keep track of whether we have rejected a request. So remember when we talked about response ports rejecting a request and having to keep track of doing so that they can send a retry later in the future. So we're going to keep that as a Boolean, as a private member of simple memory object. And we're also going to keep track of a blocked packet. So for example, since this is a response port and the requester might not have the receiving bandwidth to receive the response, we are going to keep track of that rejected response in the blocked packet. So packet pointer is mostly what we will use to create packets and pass them around. So we're going to pass around pointers to places in memory. And so that packet is is implemented in include mem packet.hh, but you don't already have included port.hh, which includes packet.hh. So, but just to be clear, packet definition is in mem/packet.hh. And then we need a constructor for the CPU side port, which, so if you go to the response port constructor, it needs a name, so a string, to call that response port, and a pointer to a SimObject that owns that port. So again, we already are keeping track of SimObject, simple mem object star, which is of type SimObject star. So we can pass that to the constructor of response port. And now in the constructor, let's initialize the things that we defined. We're going to initialize owner to the owner that we received from the constructor. We're going to set need retry to false, because initially the response port hasn't rejected anything. And we're also going to set blocked packet to null pointer, because initially, again, the response port doesn't have any responses being rejected. Now let's take a look at a few functions that we need to implement. So one important function of both types of ports is the get address ranges. It is more important for response ports because it is the function that tells other SimObjects in the system what addresses this port is responsible for. So for example, imagine you're implementing a crossbar and you want to decide where to route a packet, and you have multiple ports on one side. You want to be able to ask from each port, what addresses are you responsible for? And this is what you will do to get those address ranges. So interesting thing here is that both request and response have this function. However, you only need to implement that for your response ports, because when you call get to address ranges on a request port, it'll call the get address ranges function on its peer response port. Does that make sense? Are there any questions? OK, great. So we're also going to add our own function called blocked to return whether this port has been blocked, which basically means whether the blocked packet is a null pointer or not. And we're also going to implement a send packet function that sends the packet. So it's a wrapper around send timing response. OK. And we're also going to implement this public function, again, try, send, retry, to send retries whenever we see fit. And now there are a bunch of functions that you have to implement for this class to not be abstract. Again, get address ranges is one of them. Like your simulation is not going to work if you haven't implemented this function. Receive atomic basically is responsible for handling memory packets in atomic memory access mode that we talked about. In this session, we're just going to panic whenever we get an atomic request. So don't worry about it for now. But this is where you want to do whatever it is that you want to do when you see an atomic request. Receive functional, again, when we receive a functional access, we're going to call the port going to call receive functional. And the most important thing that I want you guys to focus on is receive timing request that we saw. And it's going to take a packet, and we're going to see how we're implementing that. And we're also going to implement receive response retry, so that in case the requester sends us a retry, we can handle that. OK, any questions from response CPU side port?
So where exactly are we tracking the packets that has been blocked?
In the blocked packet. So whenever we receive a false, so sorry, this way. OK, so whenever we receive a false here, sorry, let me use the mouse pointer. Receive a false here, the responder is going to assign the pointer to that packet that it was trying to send to blocked packet. Like this is how we're going to implement it.
Shouldn't it be data structure like an array or
Sorry.
the pointer? Are we keeping track
Yeah, exactly. Yeah.
What if the response port cannot handle
So yeah. So for this specific SimObject, we're doing one packet at a time. So there's only one packet on the fly as we go. So there's no need to keep track of multiple rejected packets. But if that keeps happening, you have to have some internal like FIFO or a queue structure to keep track of all the packets that are rejected, right? So since one packet is rejected, that's like the first entry in your queue. So every packet that you receive is going to be pushed back to the back of that packet. Does that make sense? Yeah. Okay. So for the purposes of this SimObject, we're not going to have that because we're only accepting one request, and we're waiting until we get the response to be able to receive another request. So we're never going to have any like queue inside the simple memory object. Okay. Any other questions? Okay. Mem side port again. We kind of define the same things, but one thing that I want to mention here is that I don't have a need retry for the mem side port, and there's a specific reason for this. So you should never reject a response that the memory sends you. And this is how things are also done in real hardware. So the memory controller is kind of a dummy structure compared to the CPU that requests for data. So the data should make sure that it has the, so the requester has to make sure that it has the receiving bandwidth for a request before it makes that request. So we are never, ever going to respond false when we're receiving a response from memory controller. Does that make sense? Is that clear? Again, the same blocked function to make sure that we might have a request that is rejected this time. And we also have receive timing response, receive request retry, and receive range change that are the particularly essential functions that we need to implement. And what we're going to do is instantiate one CPU side port named inst port. So this will be parallel to this, this line, or this port will be parallel to this port. So CPU side port inst port is parallel to inst underscore port. CPU side port data port is parallel to data underscore port, which is a response port. And mem side port mem port is parallel to mem underscore port, which is a request port. Okay. And then we're going to have a Boolean member. So we define two classes, mem side port inside the body of the class simple mem object, and CPU side port. So let's just retract those definitions. So these few lines include all the definitions or declarations that we need for those ports. But let's see what members we need for the simple mem object. So we need a blocked Boolean to keep track of whether we have an on-the-fly request. So whenever we have made a request or received a request, we're going to set block to true so that we reject all the incoming requests until we receive the response for that request. And then we're going to come across needing a bunch of functions that I, as an Oracle, have put here. So we're going to see why we need these. So let's not worry about these right now. But now let's, apart from the constructor, look at this function that we have to implement now that we have ports. So again, for gem5 to be able to draw parallels between ports in Python and ports in C++, we need to tell gem5 what port from C++ is the equivalent to what port from Python, if that makes sense. So and see, we're going to see how that works. So let's go ahead and actually start implementing things. So if you open simplememobject.cc, you're going to see a list of to-do items that you are required to implement to get this SimObject done. Before that, I want you guys to uncomment these to-do items and delete the to-do. So let's do this together. Okay. And I also forgot to build for So any question? Okay. So I really want to caution you guys about uncommenting the scan script, because please don't do that right now, because if you do that, it's going to try to build our simple mem object, which is not complete yet. It's going to give you compilation errors. I'm hoping that you guys compiled it beforehand. So I don't think you guys are going to run into that issue, but please do not uncomment the lines in scan script in simple mem object. We're going to uncomment them when we complete the implementation. Okay. Yeah. Yeah. Okay. Yeah. Okay. Yeah. Okay. So because we're falling behind, I'm just going to show you the implementation from the completed code, and we're just going to copy and paste. So the get port function, so again, it's useful for you to go back and forth between Python and C++. So the get port function takes two arguments, an interface name and an ID. So forget about the ID right now. It's a different thing. We're not going to be concerned with it right now. So we're going to ask Python what port you want me to give you. So if the name of that port is inst port, remember what we called that instruction port in simple mem object, inst port. We're going to give it back the instruction port that we instantiated in C++. If the name is data port, we're going to return data port. And if the name is mem port, we're going to return mem port. And if the name is something else, we're just going to tell our parent object, I don't know how to handle this. So we're just going to return SimObject : get port. Okay. So let's just copy and paste this from the completed folder. Or you guys can basically copy and paste the whole file instead of doing this. But OK. So receive functional. So receive functional is one of the easier functions that you have to implement on every response port. So remember, we kept a pointer to the SimObject that owned this. We're going to call handle functional on the SimObject. The port is going to say, hey, I don't know how to functionally handle this. I know you know how to functionally handle this, or you are responsible to handle this functionally. So I'm just going to. So we're just going to call owner handle functional. So it is one of the functions that we uncommented from .hh. I believe it's the first one. So this is something that you have to come up when you're designing a SimObject. It is not a function that is defined by SimObject. This is what I named this function. You can call this blah, and it still works. OK. So get address ranges. Again, I talked about response ports being responsible for returning the address range they're responsible for. So this now is very specific to the design that we have in mind. So the address range that our simple mem object is responsible for is basically the address range of the memory object that the simple mem object is connected to, right? So again, where the response port is going to tell the owner, hey, can you please give me the address range I'm responsible for? So the owner again, we will call return the owner getAddressRange function. So let's do this again. So, and now let's look at the handle functional. So when you so in order to implement the handle functional on the owner, you just basically call handle functional on your memory side port, which basically passes implementing handle functional to the next object, until it reaches some place that actually implements handle functional, right? It's a series of function calls, and it finishes at the final responder in the system, which is probably the. OK. So again, getAddressRanges, now we have to implement that for the simple memObject, right? Remember, getAddressRanges for the CPU side port calls getAddressRanges for memObject. We're again going to ask memory port to give us its address ranges, and we're going to return that. It's simply going to call memport.getAddressRanges. So remember, memport was a request port. So what did request ports do when they had getAddressRanges called? They would call getAddressRanges on the response port. In this case, the getAddressRange, so the response port is connected to the request port on simple memObject is the response port of memory controller. OK, so this is how we get the address range the memory is responsible for. Yeah.
So you might ask, why do you call getAddressRanges if you're just like passing around? So on the final responder, say on a memory, you're going to have multiple memory channels. Some memory channels are going to respond to some address ranges. Other memory channels might respond to other address ranges. And you're going to include having like interleaved address ranges where like the interleaved bit is like the 7th bit or something. So you're going to have one cache block over here, one cache block over there, that kind of thing. We'll talk a little bit about interleaved address ranges on it. Right?
Yeah.
But yeah, you need this because some objects might only respond to a subset of the address ranges.
OK. So send functional. OK. So when so now we also have to implement a receive range change. Basically, whenever a responder has a change of the address range it is responsible for, it has to let the peer request ports that my address range has changed. So you might want to change your routing table internally. I'm just letting you know that my address range has been changed. So what we're going to do, because we are not doing any routing, we're just going to send that range change notification to CPU. Or first, we're going to send it from the port to the simple memObject, and then from the simple memObject to the CPU. OK. So simple memObject send range change basically calls send range change on instruction and data port, which already have these functions implemented. Again, these two functions are these two ports are now telling the CPU that, hey, we have observed a range change. So now it is your responsibility to pull in all the ranges that you need or update your routing table. So in the implementation of receive range change in a CPU, which is the ultimate requester, it's going to again call getAddressRanges. So OK. So now we get to the interesting part, which was the receive timing request on the response port. So let's see how that is implemented. OK. Let's just copy and paste it here. OK. So what this response port is going to do is ask the owner whether it has the receiving bandwidth, right? It has received a packet, but doesn't know if the owner SimObject does have the receiving bandwidth. So we're going to implement this handle request function that from the SimObject that tells the ports whether it can receive that, that packet. So how it should be implemented. And I'm just going to copy and paste this. And let's just go back to our design. Let's look at what we wanted to design. OK. So we wanted this SimObject to only forward requests one packet at a time. So if there is a request that is on the fly, somewhere in the system that hasn't been serviced yet, we're going to reject that request. So there are four conditions that might be true, right? For example, if the SimObject itself is blocked, right? So whenever we receive, you're going to see what this blocked means. So whenever the SimObject receives a request, it's going to set that blocked to true so that it keeps track of it having a request on the fly. Or the memory port is blocked. So if the memory port was unable to send that request to the memory because the memory didn't have the receiving bandwidth, we should not try receiving another packet. Okay. Or if the instruction port was blocked. So remember, instruction port was a response port. So for example, if the CPU had requested an instruction to be read, but didn't have the receiving bandwidth for that instruction and had rejected that instruction read, the response port should keep track of that blocked instruction, and we should not accept a request until that rejected instruction is out of the pipeline. Or if the data port with the same argument has been blocked. So if any of these conditions are true, we're going to reject false. But because of the way that we're designing the system, I have a guess that neither of these ports are going to be blocked. OK, but let's add a printf statement to say that we have received a request for some address. We're going to print the address of the packet by calling getAddr. So it has a function called getAddr that gives you the address it's responsible for. So if we now have the receiving bandwidth, let's just set the blocked to true so that we know we have a packet that we're working on. And then let's just forward that packet to memory port, which we do by calling sendPacket on memory port. And then let's return true. So we took the packet, we read the address, we set our internal bit to true to know that we're working on something, and then we sent it to memory, and then we told the CPU that, OK, we got you. OK. OK, now let's implement the sendPacket, which basically calls send timing request. Remember those exact same names. OK, we just make sure that we never call this sendPacket when blocked packet is not null pointer. So if we have a blocked packet, we should not try to send another one. OK, so we're going to panic if blocked packet is not equal to null pointer. OK, and then if send timing request fails, we're going to set the blocked packet to packet. This is where Jason was talking about that the requester is responsible for keeping track of the rejected request, right? Because the response port did not receive the request, we're going to keep track of it here. So whenever the response port sends a retry, we're going to send this back, send this again. OK, so great. Now let's implement the retry process. OK, the retry process. So we should never receive a retry from the response port if we are not blocked, right? If we haven't been blocked by the response port doesn't have a reason to send us a retry. So these assertions are really good for you to use to make sure that you're implementing the correct functionality. I highly recommend them because they have been very useful for me when I implemented SimObjects. Let's again add a statement to print that we received a request retry. So basically, we're printing that, OK, I received a request retry from a response port. And now I'm going to try to send that. What we're going to do is copy that blocked packet into packet and send blocked packet to null, right? And now we're going to send this packet again. So there's a chance that this send packet fails again, which in turn will set blocked packet to that packet again. Okay, so this is why we had this temporary variable called packet, so that we can set blocked packet to null in case it succeeds. And if it does not, it will be reset to the same thing it was. Okay, now we have reached the place where we receive responses. Again, the good thing about ports is that you don't have to implement the functions inside the ports. You just delegate that to the owner SimObject. The port is going to, I don't know what to do with this response. I'm just going to let my owner know that I received a response, which basically requires to call handle response on the owner SimObject, which is one of the functions that we uncommented from the HH file. So what I want you to pay attention to is that these functions might come up as you try implementing these interfaces, right? I needed to implement functions like handle request, handle response for the SimObject. And depending on what design you have in mind, you might want to treat responses and requests differently. Okay, so what we're going to do is that if we received a response, it means that we previously have made a request, right? Which means that we should be blocked. Like the blocked Boolean should be set to true. And then let's, again, we print something. We print that we received a response. False, right? We have received the response. And now we are, as far as the simple mem object is concerned, it's with that packet. However, it might try to send the response back, and those ports might be blocked, which is why we check for ports being blocked here. Okay. Okay, so we have received a response. We have to figure out where to route it, right? So if it's an instruction fetch, we're going to route it back to the instruction port. And if it's not an instruction fetch, we're just going to route it back to data, right? So the only case that this packet could belong to the instruction port is if the packet was an instruction fetch. Okay, so now remember when we talked about when port rejects a request, it has to remember that it has to send the retry in the future. So that's what we're going to do. So we're going to tell instruction port and data port to send a retry to CPU in case they have rejected a request from CPU before. So the same thing, the same kind of implementation applies to receive response retry as receive request retry. But let's take a look at receive try send retry. So in try send retry, which is the last function, we're just going to okay. So if the need retry Boolean is set to true, which means that previously we have previously rejected a request. And if the port itself is not rejected, meaning that there is no response that the port needed to send back to the CPU and was rejected, we're going to now tell the CPU to try to send that request. OK, so one interesting thing is that before we send the retry request, we're just going to set need retry to false because we're going to do that in the future. One interesting thing is that we're calling try send retry on both data port and inst port at the same time. And the chances are they might have blocked something at the same time. So when you call this, the condition for both of them might send a retry, but one of them is going to go ahead. So like CPU will get a retry on both the instruction port and data port, but one of the instruction or data is going to go ahead. Since we're calling the instruction first, it's probably the instruction is going to go ahead. OK. Now we're done with implementing this simple mem object. Sorry we couldn't do a hands-along session. But let's recompile gem5 by uncommenting the scan script. We're just the same, which is kind of the same file as before, just the names of the SimObjects and the paths have been changed. And let's just recompile gem5 for x86. OK. Is it OK if we go 5 minutes over? OK. Is it OK? Yeah. OK. OK. So we went over all of this material. So if you want to see how the function calls look like, please look at slide 51. And this is how things look like.
So while we're waiting for that file, I'll say this seems quite complex. And actually, this is a very simple right? It completely blocks if something is outstanding, and it's like not a cache or anything just forwarding around. But hopefully this gives you an idea of how you might be able to slot in around stuff. If you want to go deeper, on the gem5 website, if you click documentation and go to learning gem5, and then modifying and extending, there's a whole example that goes through a cache implementation. Still a blocking cache. It's not super interesting, but it's a little bit more complete example.
Yeah. So I also have included that in simple cache object, which is another directory next to simple mem object. And the completed version for that is also included. OK. OK, well, great. Gem5 is compiled with x86. And since we don't have time to... Oh, sorry. Candidate is bull. Oh. Handle request error notice. Sorry. OK. Oh, no. OK, great. Yeah, yeah. So I'm going to cheat and copy the completed version. Oh, OK. 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 Yeah, the names are a little different, though. OK. OK. Oh. So I'm going to cheat a little bit and use gem5 x86, but you guys shouldn't do it. Bootcamp, simple memObject, run simple memObject.py. OK. Great. Yeah, yeah. OK. Let me just enable one flag, which is, I guess, simple memObj. Okay.
Which needs fixed and stuff. But use your gem5.out.
Okay. What happened? Ah. Okay, great. So if you fix the compilation errors that we got, this is what you're going to see when you run that script, run simple memObject with the debug flag simple memObject enabled. So you can see that, okay, yeah. Yeah, so before, let's just see the output. Okay, so you can see that it receives a request and then gets a response, receives a request, gets a response. So you don't see interleavings of got a request and got a response. So it's like exactly one request is received, then one response is received, one request again, one response, one request, one response. Okay, now let's take a look at run simple memObject.py. Okay. So what we're here creating is again, a special SimObject called system. System has a few parameters that you set. Clock domain, which sets the clock frequency for your system. We're going to create a clock domain from source clock domain. There are different types of clock domains that you can create. You can, I think, take a look at it at clockdomain.py. If you do control P clockdomain.py, it should come up. We're going to set the frequency to 1 gigahertz. We're going to create a voltage domain for that clock domain, which we will do by just calling the constructor. One important thing to note here is that you should always specify the memory mode for your system. So the system SimObject, if you go to the definition, has a parameter called memory mode or mem_mode that doesn't have a default value. Or, sorry, has a default value that is not timing. And if it's not timing, you're not going to see time change as things are scheduled. And then we're going to create a memory range for our memory. So it's of type address range. So remember when I told you almost everything is a SimObject in gem5? These are the things that are not SimObject, like source clock, like clock domain, address range, voltage domain, and ports are not SimObjects. We're going to add a CPU to our system, which we're going to use timing simple CPU. You guys have been using this in different ways. We're going to add our own memObject, which is simple memObj. Well, you guys should see it as simple memObject. And we're going to connect our iCache and dcache ports from the CPU to the instruction and data ports on the simple memory object. So remember when I talked about ports being connected by putting an equal sign? And then we're going to create a memory bus to connect that simple memory object to the memory controller. So what we're going to do is connect memsite from memObject. You guys are probably seeing memport, which is fine. That's a slightly different, so it's a different name, to the CPU side ports of the membus. So CPU side ports are a type of ports called vector response ports. So if you go to system to crossbar UI, you're going to see the definition for CPU side ports. And then we're going to connect the interrupt ports on the CPU to ports on our membus. So please ignore this. We're going to create a memory controller by calling the constructor of the memory controller SimObject. We're going to give it a memory interface, which is DDR3 1600 8x8. That interface needs a range of addresses it's responsible for, which we're going to pass that 512 megabyte address range that we created, this one. And then we're going to connect the port on memory controller, which is the response port, to the request ports on the membus. And then there's a specific port on the system SimObject called system port that is used for debugging and functional accesses. So you just need to connect that to the CPU side ports on your crossbar. We set the binary, blah, blah, blah. We run this, and we get that beautiful STD out. Sorry, I went over 9 minutes. And is there any questions?
Yeah, why are you before we've set like an SE workload, the different function call?
Yeah, yeah.
What's the difference between some?
So the scripts that you previously saw are part of, like, developed by gem5 standard library. And what standard library does is automate most of these port connections for you. So since I opted to not use standard library for here, I have to manually do this. But if you look at the code for the standard library, you're going to see that it's doing the same thing, but in different places.
Yeah, to say that, so this is using like a bunch of raw SimObjects, whereas the standard library is giving you a nicer these kinds of things. So if you like look at the set SE workload in the standard library, it does exactly these things. Any other questions? Definitely know we went a little bit fast there. Yeah. So one other thing that I want to point out. Sorry for scrolling. So these things here, these lines. So you declare the inst port and data port in your memory object. And then in Python, when you say equals, that's going to make it so that when the CPU decache port calls sim timing request, the receive timing response will be called on the data port. So this equal sign is not setting a value, but we've overloaded it in Python, and it's just setting a pointer between these two ports. There's a little bit more complexity going on in the back end that I can show you if you're super interested. But yeah.
You have to keep track of the request from the response part.
No.
So request and response can go in either order. However, you must connect a request to a response. If you try to connect two response ports together, it will give you an error. Good question. Any other questions?
Definition, we have owner. Here, how owner is defined.
So in this case, the system.memon, since the inst port is a child of, or sorry, inst port is a parameter of memon. So when that memon is instantiated in C++, that's when the constructor for inst port will be called.
Yeah.
And it will pass in a pointer to memon.
Yeah. So let me show you the.
Indicating that you are part of this particular system of memon.
So that way the code in inst data port will have a pointer to the object that it can use to call functions.
Yeah.
It's a really good question.
It just knows that which object I have.
What particular instance of a SimObject is owning this? Yeah. Any other questions? Okay, cool. Let's do some lunch.